By the end of the 19th century, most scientists understood the components of the atom, but no one knew what the atom really looked like or how it behaved. In the 1920s, scientists made breakthroughs that have changed our understanding of the universe. In the early 20th century, scientists were struggling to understand the structure of atoms. The British scientist Ernest Rutherford and his colleagues at Manchester University visualized them as negatively charged electrons circulating about a positively charged nucleus. The German physicist Max Planck suggested that energy emitted or absorbed by an object could be emitted or absorbed only in discrete amounts or units. He called these units of energy quanta. Niels Bohr, a Danish physicist, visualized atoms much like our solar system, with the nucleus a sun and the electrons orbiting it. He called this the planetary model and applied Planck's idea of quanta to the behavior of electrons surrounding the nucleus. He suggested that electrons' orbits depend on their amounts of energy. When an electron absorbs energy, it jumps from an orbit close to the nucleus to one farther away, and when it moves closer to the nucleus, it emits energy. In both cases, the energy is in discrete quantities. Louis de Broglie, a French physicist, proposed that electrons were particles and a form of energy that acted in a wave-like manner. With more evidence, scientists realized that atoms were not like the solar system at all, because electrons did not circle the nucleus in regular orbits. In one of the most significant developments in 1927, the German physicist Werner Heisenberg showed that it was impossible to determine the precise location and velocity of an electron at the same time. All he could do was describe the probability of the location of electrons. This has come to be called the uncertainty principle. All of these ideas have come together in what is now called quantum theory or quantum mechanics, one of the most important scientific advances of the 20th century. This theory is fundamental to chemistry because the properties of elements and the way they react with other elements depend on the behavior of electrons. The uncertainty principle holds that it is impossible to know the position and velocity of electrons at the same time. All we can do is describe the probability that an electron might be found within a specific region. However, electrons with a given energy follow predictable patterns around the nucleus, or atomic orbitals. Chemists picture the orbitals like clouds that are dense where the electron is more likely to be found, and less dense where it is less likely to be found. Each atomic orbital can be described by a set of 4 quantum numbers. The principal quantum number is n. As n increases in value, the atomic orbitals grow larger, and the electrons are farther away from the nucleus. As atomic numbers of elements increase, their electrons have larger orbitals, and the size of the atom increases. Orbitals with lower principal quantum numbers have lower energy. Electrons fill the lower energy orbitals before the higher energy orbitals. The second quantum number, L, refers to the shape of the orbital. 4 important shapes have slightly different energy. All s orbitals are spherical. p orbitals are dumbbell-shaped. And the d and f orbital shapes are more complicated, as shown in these drawings. The third quantum number refers to the orientation of the p, d, and f orbital. And the fourth quantum number refers to the spin of the electron, which can be thought of as spinning on its axis in 2 possible directions. This means an orbital can only accommodate 2 electrons, each spinning in opposite directions. So the energy of an electron orbital is described by the principal quantum number n and the second quantum number L together. As n increases, there is more than one orbital shape. For example, where n is equal to 2, s and p orbitals exist. S orbitals have lower energy than p orbitals and fill first. At n equals 3, d orbitals with higher energies than p fill last. This diagram shows how the orbitals of the elements from 1 to 10 fill with electrons, filling those of lowest energy first. The p orbitals take 1 electron each, and then pairing begins. All the elements repeat this step, called Hund's rule of maximum multiplicity. Look at oxygen, element 8. A neutral oxygen atom has 8 electrons. The first 2 electrons are in the first energy level, or the s orbital. The next 2 electrons are in the second level s orbital, and the remaining electrons fit in the second level p orbital. With an understanding of the structure of atoms and the behavior of electrons, it is possible to predict with great accuracy how elements behave and combine. This is one of the most remarkable achievements of modern science.